Thanks for tuning into this Revision Zone Maths video. In this video, we're going to be thinking about limits. So let's begin with a definition. So what do I mean by a limit? Well, I'm going to give a very simple definition, which is if it exists, and that's a big if because limits don't always exist, right? It is a number. Now, you might look at this and you might say, well, this is a very vacuous looking definition. There isn't really a lot there. It is a number. I should finish this, right? And you'll be right. The technical definition of a limit is actually quite involved and certainly not suited for A-level. However, because the concept of limit is sort of used quite a bit in A-level, then it's worth having this discussion. So let me try and fill in my definition by sort of writing down some questions and trying to answer them, right? So one question might be, well, what is it good for? What is a limit good for? Right? And I'm going to give a very short, brief answer, which is it allows us to get an answer for the calculation 0 divided by 0 in some special cases, right? So it's not always possible to work out the answer of 0 divided by 0. It's only possible in some special cases. And that alone should actually surprise you quite a bit because any division by 0 it's a mathematical fact. It's not really defined, but there are some cases in which you can sort of sidestep and still get an answer out. But the answer obviously comes with caveats, right? So so what is it good for? We've answered that. The second question might be, how do I calculate it? How do we calculate it, right? And the answer is basically by approximation. By approximation, right? More precisely, we show that the error in our approximation, I'm not going to write the full word, I'll just say approx, can be made to be as small as we like. As small as we like. So a good way of doing this is actually with an example, say. So suppose I actually want to calculate 0 divided by 0, right? And of course, if you put this in a calculator, you'll get maths error. You put it in a computer, you'll get maths error. You give it to a mathematician and he'll say it's undefined, or she'll say it's undefined. It's not possible to do this like this. However, we could now consider something of the form x divided by x. Consider x divided by x, right? For x equals 0, of course, this gives 0 over 0, right? So can we in some way use x divided by x and possibly get an answer for 0 divided by 0 in some sense? The answer is, with the concept of limit, we might not be able to get a perfect answer, but we might be able to say something which is a bit more meaningful than we can say nothing, right? So let's have a think about this. So x divided by x is actually 1 for all x which are non-zero. That's definitely true because you can do that division and the answer is 1. Another way of doing this is just to apply the rules of indices and you get x divided by x is x to the 0 and the answer again there is going to be 1. However, what we can now do is since we want to work out 0 divided by 0, let's not do 0 divided by 0. Let's do something small divided by something small, right? So let's now look at approximations. So let's do 0.1 divided by 0.1. Well, what's the answer to that? Well, it's 1. Let's have a better approximation to 0, which is 0.01 divided by 0.01. Well, what's the answer to that? It's 1. Let's have an even better approximation, which is 0.001 over 0.001. And what's the answer to that? Well, again, that's 1, because we can explicitly do that calculation. And the point is, we can keep on repeating this, and the answer is always going to be 1, regardless of how small a number we take, right? So clearly, in some sense, if I do 0 divided by 0, right, I'm going to get 1. But the point is, it makes no mathematical sense if I put an equal sign here for lots of technical reasons, right? So instead, the way they work around this is they don't put They don't put an equal sign. They actually have an arrow, right? It's called the limit arrow, and they indeed don't say 0 divided by 0. What they say is they say x divided by x, right, tends to 1 as x tends to 0. Now, the point here is the approximation calculation that we've done is actually stable, right? Here, the limit exists because the approximate calculation is stable. I'll say more on this. Let's consider an example where we try to do the same thing as we did in the last example to try to come up with an answer for some division by 0, and we'll see in this case that the approximation is not going to be stable. So let's take something up the form 1 divided by 0. That's what we want to try and work out, right? We can't do that directly, so let's consider 1 divided by x, right? Where we technically say x is non-zero, because if we could put x equals 0 in, well, we wouldn't have to do this example. So then we say, okay, consider an approximation to 1 over 0 by taking smaller and smaller x, by taking ever smaller values for x, right? And we can completely do that. So I can try 1 divided by 0.1. So in this case, we're going to get 10, right? And then I can say, well, okay, I want my x to be even closer to 0, so I can try 0.01. And in this case, the answer is going to be 100. And then I can say, well, I still need to get closer, so let's try 0.001. And in this case, the answer is going to be 1,000. And you can see what's going to happen. Each time I make the denominator smaller, the answer is going to get bigger, right? So the key point here is the answer here is not the same as the answer there, and it's not the same as the answer there, right? The approximation calculation is not stable, is not stable in this case, right? Whereas in the last case, we always had 1 as the answer. It doesn't matter how close we were getting to x equals 0 without it actually hitting 0. We always had 1 as the answer. So the approximation calculation was actually stable. In this case, it's unstable. So we say the limit does not exist. Does not exist. So in other words, 1 divided by 0 actually cannot be made sense of, mathematically. So let me just write that. Cannot be assigned a value. So to just sort of write down a summary of what I've said. Summary, a limit is a number, right? It doesn't always exist, right? When it exists, so I should perhaps do the so when it exists, it allows us to say something about a calculation of the form 0 over 0, right? But when we say that, we don't say the answer is equal, we say the answer tends to, okay? And lastly, we calculate it using approximations. We calculate it using repeated approximations. And I should say in red, perhaps, only when the approximations are stable. So only when the approximations, the approximation calculations are stable, do we say, do we say a limit exists? So the question is, why do we need the concept of a limit? The answer is because the definition of differentiation requires it to be so. Because the definition of differentiation demands it, right? What do I mean by that? Well, let's look at the definition of differentiation. So let me write that down. So we have f of x plus h take away f of x, right? And then we divide this by h and we evaluate the limit as h tends to 0. Well, you might look at this and say, well, okay, the h tends to 0 is only there because we've put it there. So we can just redefine it to not have h tends to 0. We can just redefine it to be in some sense this sort of fraction on the outside. Uh, okay, that is one way to go, but that's going to leave us wanting in lots and lots of ways. The more we sort of start to think about it. So we do know that these things come from curves. So I've got some sort of a curve. So I've got y and x, and I've got a point here, and I've got a point here. Say, let me actually mark the points in slightly different colors. So I've got a point here, and then I've got a point here, right? And the point can be sort of written as, say, the red one can be x and f of x, and the green one can be the slightly higher one, so it can be x plus h, f of x plus h, right? Now, if we were to say that we were not going to take the limit, then what that means is when we look at our gradient, we cannot get the gradient of a tangent. So let me write that down. If we do not take the limit as h tends to 0, then perhaps I can tidy that up. We cannot work out the gradient of the tangent to y equals f of x at xy, right? The best we can do, is to work out the equation of some line, or maybe the gradient of some line, perhaps I should say, rather than the equation, to work out the gradient of some line passing through 2 points on the curve, passing through 2 distinct points on the curve. Yep, and the 2 distinct points are quite clear, the red one and the green one. Okay, so we do need the limit concept from that standpoint alone. The other reason why we actually need the limit concept is, let me actually say this at the bottom. So let me sort of say reason 1 here, and let me say reason 2. is so to arrive at a place where we want to, for example, have a tangent, the gradient of a tangent at a point, what we basically want is we want our blue triangle to get smaller and smaller and smaller because the green point has to get closer and closer to the red point. But as the green point gets closer and closer to the red point, watch what happens, right? So as green point, which is obviously x plus h, f of x plus h, right, gets closer to red point, which of course is x f of x, we have h getting closer and closer to zero. So the concept of limit is already creeping in the minute I start to do that, right? The concept is somehow already there. But as h gets closer and closer to zero, so I should say consequently, there is only one point. One point. What do I mean by that? What I mean by that is as h gets closer to zero, then x plus h over f of, not over, sorry, x plus h, f of x plus h actually gets closer to just x f of x, right? Because the h is going to become sort of so small and become effectively zero that it's going to start to disappear from there. And when it disappears from there, the point you get is just x f of x. So in other words, and I'll say this in maroon at the top actually, as h gets closer to zero, you have f of x plus h take away f of x over h actually starts to look like 0 divided by 0. It starts to look like 0 divided by 0. Why should that be the case? Because if you have a think about it, if that h there becomes 0, if that h there becomes 0, then the numerator becomes just f of x take away f of x, and that's obviously 0. And if the h becomes 0, well, then the denominator, of course, is going to become 0. Then you start to have something which looks like 0 over 0. So the notion of a limit actually comes back. It comes back at the very heart of the definition of differentiation. So just to make sure that the point is crystal clear, so we need the notion of limit because in the very act of actually getting a gradient of a tangent as opposed to a gradient of a line passing through two distinct points, uh, and obviously the second point is the notion that as I move the green point closer to the red point, we actually have the green coordinate become the red coordinate, right? And the moment you have that, when you start to try and work out a gradient, which I'm trying to do here, you get back to a calculation of the form 0 divided by 0. So the entire concept of limits is formalized as a way of handling this sort of a thing. Now that we have some understanding of what a limit is, what it tells us, how we calculate it and decide whether it exists or not, it's worth knowing some standard limits from the A-level syllabus. So let's think about the first one. We can do these as examples actually. So let's just say example, and this is the first example. So we want to be able to calculate the limit as h tends to 0 of e to the h minus 1 over h. We want to know what this is as a number, right? I can tell you it definitely exists. So let's try and work it out together. So let me say solution, even though I've not quite put a question down, but you know what I mean. So what we have is we want to basically think about this function here. The function is e to the x minus 1 over x. Why this function? Because if I put h into this function, right? So f of h, for example, I would end up with the exact thing I'm trying to get the limit of. So I'll get this. What do I actually want? We want value of f as h gets ever closer to 0, right? Now, So one way of doing this would be to go and say just put 0 in and let's see what we get. In this case, we're going to get e to the 0 minus 1 over 0, which of course is going to give me 1 minus 1 over 0. Well, the minute I actually had a 0 in the denominator, we had a problem because division by 0 is not defined. But if I nevertheless run through what the numerator works out to be, I get 0 over 0. And this is undoubtedly undefined. So I can't just actually work out an answer in this case like this. But the strange thing is if we go to the graph, I've actually got the graph of the exact same function. And look, at x equals 0, the y value is 1. So in some sense, we can say something sensible. We don't get an infinity coming out of this or something crazy. So how did the computer work that out? Well, what the computer did was it worked out a limit. It basically worked out the approximation to 0. It said, well, what would it be at 0.1? And it got some number. And then it said, well, what would it be at 0.01, which is closer to 0? And it got another number. And then what would it be at 0.001? And it got another number. And the computer figured out that these numbers were actually going to be stable, and they were going to be stable. Because they were stable, the limit actually existed, and we can now go back to the initial statement and actually put a 1 there, right? So we've actually been able to work out what our limit was actually going to be. The limit's going to give us 1, right? And this is again reassuring because that's exactly the value we see on the graph. So let's look at example 2. What do we need to figure out in this case? Well, in this case, we want to work out the limit of sine h over h. And I can tell you this definitely exists, right? And it's very important. So let's work it out. Well, we need to define a function which is going to be able to mimic the thing we want to work out the limit of. So we're going to define a function called, say, g of x, and we're going to call it sine x over x, right? If you see on the right-hand side, we've already got a graph of g of x. Uh, so I am going to come to the graph slightly later, but for now, let us continue thinking. Well, let's just check. G of h is actually going to give us sine h over h, which is the sort of thing we want to work out the limit of. So to be able to work out the limit as h tends to 0 of sine h over h, I've basically got to work out the limit as h tends to 0 of g of x, right? So I'm writing this in slightly more abstract and formal language than I did in the last example, but this is pretty much what I said. So once we have this, well, one way of working this out is to say, well, let's try to work out the value of g at in x equals 0 or h equals 0, depending on how you want to be thinking about this, whether you're thinking with with sort of this function here, whether you're thinking with that function. It's the same function. So let's put 0 in. When we put 0 in, we get sine 0 over 0. Well, the fact that there's a 0 in the denominator should already tell us there's a problem. But even if we evaluate the thing without worrying about that, we get 0 over 0. Well, this is clearly undefined, as we know. But this is precisely why we need the notion of a limit, because in this case, we can say something meaningful about this, right? So I could again now go and say, well, how are we going to work out this limit? We're going to work out g at points close to x equals 0, so maybe 0.1, and then g at 0.01, and then g at 0.001, and then work out the output values of the function. And once we've got the output values of the function, we could maybe check to see if these output values are going to be stable. And of course, they are going to be stable, right? But we need not even do all of that. Why? Because we have a graph. And the graph already tells us. In fact, I can go precisely to that point on the graph. The graph tells me. The graph tells me as I put a half in there, I don't quite get 1. I get something close to 1. But the closer I get to x equals 0, I actually end up at getting the value of 1 as an output to g. So what is this limit going to be? This limit is going to evaluate to give me 1, right? And this is a very important fact, so perhaps I should put this again in a red box to emphasize its importance. The one thing that I should actually say here is during this calculation, we've implicitly assumed that we're working in radians. So perhaps I'll write it in green at the top. To calculate this limit, we have had to work through, oops, I shouldn't write there perhaps, to work out all calculations in radians. If you try to repeat this in degrees, what would happen is these output of the function g are going to be unstable, so the limit won't actually exist. So in fact, this is one of the reasons why radians as a unit of measure was defined, because it allows us to be able to do this sort of stuff, to be able to work out limit in this case, which otherwise in degrees would not really exist. So hope you found that useful. Let's move on to example 3. So moving on to example 3, in this case, the limit we're trying to work out is limit as h tends to 0, no less, of cos h minus 1 over h, right? So again, this limit does actually exist, as it turns out. I could go over the exact same sort of argument that I've done, but I'll make this a bit more brief, right? Ultimately, the function we're going to be wanting to work with is, if I say call it t of x. T of x is our function, which is cos of x minus 1 over x. And of course, if I evaluate t at h, I get exactly the sort of thing that I want to work out the limit of. So I want to work out the limit as h tends to 0 of cos h minus 1 over h, but that's same as to work out the limit as h tends to 0 of actually t of h. But the point here is, when I put 0 into t, I get cos 0 minus 1 over 0, but cos 0 is 1, so I get 1 minus 1 over 0, which is 0 over 0. So again, we run into a problem that we've seen time and time again. So we basically work out the limit using the sort of method that we've seen before. But in this case, we need not repeat that, as I say. What I need to do is just go to the graph, because I have a graph of the very function that we're trying to work out the limit of. We can see from the graph that the x values are going to get closer to 0 than the y values are going to get closer to 0. So I know what the limit evaluates to give me. The limit actually evaluates to give me 0. And since we know that, let's put a big red box around it, because it's so important. And the only point worth saying now is this calculation is done in radians. This calculation has to be done in radians, for the same reason which was given earlier. If you do it in degrees, then the limit doesn't actually exist. So this again really justifies why radians are introduced into the A-level syllabus. To end this video, let's just look at a quick summary of the statements we've seen. Right? So we've seen that if you work out the limit as h tends to 0 of e to the h minus 1 over h, that actually gives you 1. We've also seen that if you work out the limit as h tends to 0 of sine h over h, that actually gives you 1. And if you work out the limit as h tends to 0 of cos h minus 1 over h, that actually gives you 0, right? Just to make a connection, I'll actually make a remark here. So in the last video, we differentiated the function e to the x, and we actually showed that the derivative was e to the x, but we did it all graphically, right? But now that we know the limit, we can actually do it formally. So if I go back to my definition of a derivative, the limit definition that is, right? And if I write that down, which is x plus h minus f of x, and the whole thing is over h, well, what I'm going to have in this case is, because my f of x is e to the x, I'm going to have e to the x plus h for f of x plus h, and take away e to the x. And now, using rules of indices, I can expand out the first term. So I can say this is going to be e to the x, multiplied by e to the h, multiplied by e to the x, and the whole thing is over h. I can now factorize out my e to the x from both the terms in the numerator. So I end up with e to the h minus 1 over h. But of course, because e to the x is not really part of the limit, this limit here, as h tends to 0, because e to the x is a function of x and the limit is in terms of h, I can take out e to the x, right? So I end up with e to the h minus 1 over h. And now here's where we can use the very first statement we wrote down in our summary. So perhaps I should have numbered them. Statement 1, statement 2, and statement 3. So using statement 1, we can say it's going to be e to the x times by 1, which of course is e to the x. So we've actually been able to formally work out the derivative of e to the x without using any graphical arguments. As always, we hope you found that useful. If you would like to see more videos on specific topics, then please say that in the comments. Do hit the like and subscribe buttons. Thank you for watching, and we'll see you in the next video.